So that's the basics of the impedance-only Smith chart. The other graph included in the full color chart is admittance. Note that admittance and impedance both give you exactly the same information. Impedance is the inverse of admittance and vice versa, but a given problem may be easier to consider in terms of one or the other. You can decide which values to use based on what you're trying to do. Here's the admittance Smith chart. This is exactly the same chart, except that what we're plotting is normalized admittance rather than normalized impedance. Normalized admittance is equal to the load admittance divided by the system admittance, or 1 over the normalized load impedance. All the scales around the edges and at the bottom of this chart are identical to those on the impedance chart. These are the lines of constant real admittance, or conductance. And these are the lines of constant imaginary admittance, or susceptance. Positive susceptances are graphed below the center line, and negative susceptances are graphed above the center line. This is the most important difference to keep in mind when using the admittance chart rather than the impedance chart. The imaginary part of admittance is plotted on the upper half if it is negative, and on the lower half if it is positive. The reason for this is pretty simple. A component with a negative reactance has a positive susceptance, and vice versa. So for instance, a capacitor has an impedance of negative j over omega c, but it has an admittance of positive j omega c. So to read the normalized admittance of this point off the chart, you would read the real part here, 0.4, and the imaginary part here, negative 0.6. So the admittance plotted here is 0.4 minus j 0.6. This chart can be used just like the impedance chart, except the values you're working with are admittance values, not impedance values. The full color Smith chart allows us to jump back and forth between using admittance values and using impedance values, depending on which is easier for the specific application at hand. Here's the full color Smith chart again. The impedance chart is plotted in red, and the admittance chart is plotted in blue. One of the things this full color chart makes really easy is impedance matching using LC networks. So consider this. Suppose we have a load with impedance ZL. If we add an inductor in series with this load, the reactance of the inductor, j omega L, will add to the reactance of the load. But the resistance, the real part, will not change. So adding a series inductor will move us upward around a circle of constant resistance. If we instead add a series capacitor, its reactance is negative j over omega c. So adding a series capacitor will move us downward around a circle of constant resistance. What if instead of adding an element in series, we add one in parallel? If the element added is in parallel, we can't just add impedances. The parallel relationship for impedances is more complicated than that. But admittances in parallel add. So, if we add an inductor in parallel with the load, its susceptance is 1 over j omega L, or negative j over omega L. This susceptance adds to the susceptance of the load without changing the conductance, the real part of the admittance. So if we add a parallel conductor, that moves us on the Smith chart upward around a circle of constant conductance. And if we add a parallel capacitor, which has susceptance of j omega c, it will move us downward around a circle of constant conductance. Let's give it a try. So suppose we have a load with normalized load impedance of 0.5 plus j 0.5. If we add a series inductor with a normalized impedance of j.5, we will move clockwise around the constant resistance circle by j.5, which is marked in black. The normalized input admittance after this addition becomes 0.5 plus j1. If we instead add a series capacitor with a normalized impedance of negative j 0.4, we will move counterclockwise around the constant resistance circle by negative j 0.4. The normalized input impedance to this circuit, then, becomes 0.5 plus j 0.1. Or what if we add a parallel inductor with a normalized admittance of negative j1? In this case, we will move counterclockwise along the constant conductance circle by negative J1. The normalized input admittance, Yn, becomes 1 minus J2, which corresponds to a normalized input impedance of 0.2 plus J 0.4. Finally, if we add a parallel capacitor with a normalized admittance of J 0.6, we will move clockwise along the constant conductance circle by J 0.6. The normalized input admittance to this circuit becomes 1 minus J 0.4. So the thing to remember is, if you are adding elements in series, use the red impedance chart. And if you're adding elements in parallel, use the blue admittance chart. We can apply this technique to perform impedance matching using LC combinations. Remember, a match occurs when the input impedance is equal to the system impedance, which on the Smith chart is plotted in the center. So suppose we have a load with a normalized load impedance of 0.5 plus J 0.3, which sits here, and we want to create an LC combination to match it. In other words, we want to create an LC combination that can move this impedance to the center of the chart. As a first step, we can add an inductor in series with a normalized impedance of J 0.2. This will move us clockwise along the constant resistance circle by J 0.2. The normalized impedance to this circuit, Zn, becomes 0.5 plus J 0.5. The admittance at this point is 1 minus J1. Now we'd like to move down along this line. So let's add a parallel capacitor with a normalized admittance of J1. This will move us clockwise along the constant conductance circle by J1. This brings us all the way down to the origin. So this LC combination added at the load will match the load to the network and maximize power transfer to the load. Note that we've done this design in terms of impedance and admittance values. An inductor of impedance J 0.2 and a capacitor with admittance J1. The impedance of a circuit element is frequency dependent, so this is not a broadband design. In order to find the appropriate inductance and capacitance values for this design, you would have to pick a specific operating frequency and solve the impedance equations for L and C. Also note that we could have, with equal validity, gone this route and designed this as a combination of a series capacitor followed by a parallel inductor.